All right, welcome back. So this is going to be the part two on matrix and vector calculus. So this is part two. I'm Professor Wu. Let's get started. Okay, so it's pretty easy from last lecture that we learned if we want to take the derivative and the function looks something like this, right? And we want to where x is a vector of three elements. Right. So all we have to do is take the derivative with respect to each one of them at a time. So solving this is pretty easy. You solve this one, df dx1, right? Then you solve df dx2. So these will be constant. df dx2, df dx3. So hopefully you remember that from the last lecture. So solving functions that look like this is really easy. The problem comes in when many of the problems we will be solving don't look like this. Instead, they'll look more like this. Notice how these are multiplication of vectors, right? These are vectors. Here is a vector multiplied by matrix, right? Exponential to this. So let's take this one for example, right? If f of x is equal to y transpose ax, then what's df dx? Well, well, this this was easy to solve, but now we have like vectors and matrix multiplied together. Like, how do we deal with something like this to find the derivative? Okay, so that is the point today. Specifically, we're going to go over a lot of the functions we'll be going through this semester. So these are actual machine learning uh, equations that we use in machine learning, and that knowing the derivative for these equations will come in handy later on when I teach you guys what they are used for. So, so notice how most of them are in matrix vector format, right? So they are not nicely laid out like the one that we did in the last lecture. So when they are in terms of vectors and matrices instead of nice functions that looks like this, how do you deal with them? Okay, so let's. The idea is actually really simple. Taking the derivative in high dimensional space. So, well, let's say we have something that looks this simple, right? We want to find the derivative df dx, right? We want to find a derivative with respect to x. Well, previously we learned that this could be multiplied out, right? So if y is this and x is some kind of list of variables, then y transpose x is simply equal to 2x1 plus x2, like that, right? Well, now that we multiply this out, it's pretty easy. So it's easy for you to take the derivative with respect to x1, right? And then with respect to x2, right? So with this linear form, like even though this right here looks kind of confusing, we now know through what we've learned with linear algebra how to convert this into this. And once we've made this conversion, the derivative is really easy. It's simply the continuation of what we learned last time, right? So and this rule follows, it doesn't matter what you see or how complicated the equation looks, right? Something like this that looks more complicated, but all you have to do is multiply them out through the matrix operations and multiplications we've learned previously, and then you will, as a final result, get an equation that look like this. So step one, multiply them out. Step one, multiply them out, apply the rules. Basically multiply all the vector matrix, right? Once you multiply them out, you take the derivative one variable at a time. Okay. And this is what we learned last class, so how to take derivative one variable at a time. The only addition is that if you have something that looks complicated, you just have to multiply out first. Okay, so as long as you know how to perform matrix vector operation, you can essentially always take the derivative. So over here, this was that example I told you about, right? This right here, if you just look at it, it's the multiplication between two vectors. Okay? So when we multiply out, it looks like this. Therefore, when we take derivative with respect to x1, it's 2. And then with respect to x2, it's 1, right? So 2, 1. So the derivative is just 2, 1. Okay? So there's one last step that will help you simplify these, is that once you figure out how to do this once, you can try to look for patterns. And with these patterns, you simply in the future can just use that pattern as a rule as opposed to do it the same one over and over again. So notice, right? Notice this is the derivative. So what is saying that if I take the derivative of this, we get 2 and 1. But what is 2 and 1? Notice 2 and 1 is just equal to y. So therefore, the derivative of this is just equal to y. This is very reminiscent when we have derivative of a single dimensional variable, like 2x, right? Or y times x. If y is one dimension, x is one dimension, and we take the derivative with respect to x, we just get y. And this actually follows when we're in higher dimension. We end up getting rid of x just like this, and we keep the y as the vector. And as always, the result should be a column, right? Vectors are, for our lecture and our classes, going to use the standard that vectors are always columns. Okay, so this allows us to conclude that whenever we have a derivative with respect to a vector multiplication, all we have to do is get rid of x, and there's the y. And this is always the case, regardless of how you change the numbers inside y, right? You can put other numbers in, and you're still going to be this case. Or if you have higher dimension, right? So even if you have 3, 4, 5 dimension as the vector y and x, the rule will still be the same. The derivative is simply y. Now, over here, like, it's much better when you try yourself. So let's say this is the function, and now we change the definition of x and y, right? Now, use that rule we just did, where we multiply them out, and then take the derivative. You will see that the solution is just y, right? If you do it one step at a time, the final result is y. So ideally, you've learned this, and in the future, if you see this kind of multiplication, you simply know that the derivative is y. But if you somehow forgot, you can always simply multiply it out to get the equation, then take the derivative one variable at a time. Okay, so like pause the video and see if this is true. So we're gonna go on now. All right, so for the next exercise, now that you get the point, let's do a little bit harder. This is the function, right? Now I want you to follow the step, multiply them out, right? Multiply them out. Then you take the derivative one variable at a time. And after that, maybe you can identify a pattern. So pause the video. Let's see if we can, if you guys can do this. Okay. And once you take the derivative, hopefully you can do the last step, which is to recognize some kind of pattern to reuse for the future. Okay. Pause. And now I'm going to go on. All right. So over here, if you, here's A, here's X transpose, right? So if you multiply them out, the result looks something like this. And taking the derivative of this one variable at a time is not difficult, right? So you're going to get, when you take the derivative, you should get something that looks like this. Okay? Now, well, one thing you notice that we can simplify this is by pulling x1 and x2 out. Notice how you multiply is equal to this equation. After you pull this out, there's one step that is not very obvious. However, it's always true. You can pull this out once again, such as this is equal to the summation of these two. And it turns out that this is simply A transpose A. Take a look, right? How A was defined. This is A, right? A. Take a second and look. And this turns out to be the A transpose. Now, this rule is not obvious, But it turns out to always be the rule where the derivative of something that looks like this will always look like this. Okay? Once again, you can just remember the rule, or you can always just break it down into this equation, take the derivative one at a time. Now, since this is A transpose plus A times X, what happens if A transpose is equal to A? We call that a symmetric matrix. Symmetric matrix. What that means is if you have a matrix that looks something like this, 1, 3, 3, 4, right? Now, if you take the transpose, it's still 1, 3, 3, 4. Okay, so when you have these cases, which it turns out that we very often have these, then it's just when you have A transpose A, since they're the same, it's just 2A. Okay, so that happens to be the rule. When you take the derivative with respect to this, you're always going to get this, and if A transpose is equal to A, then it's just 2A. Okay. All right. So that's the second one. All right. Now let's do more practice. Try to find a derivative for the following function. Now notice how this is just linear, right? This is linear, which is what we did earlier, vector times a vector. Over here, the exponent part is what we call the quadratic. This is called the quadratic. This equation. So we have the quadratic, we have the linear. So this right here is a matter of just using the chain rule. And over here is a combination. Okay? So try to use what we just learned in terms of how to take derivative of these and find this. Okay? Pause the video. We're going to move on. Yeah, pause the video so you can do these exercises. Okay? I wrote out the solutions for them. So if you're confused, feel free to take a look. All right, the next one. This is called the regression objective. It's one of the most used equation in machine learning, and it's one of the equations you've done before. Previously, you've done it in terms of when W and Xi are separated. Now, let's try to do them combined. Use the rule we just learned and see if you can find a derivative here. Okay? Okay. I'm going to move on. Hopefully you pause the video. Okay. I wrote the solution as well. So over here, right? Over here, I'm going to let this part and I'm going to let it be Z. So if that's Z, then I'm simply taking the derivative with Zi squared. So the 2 goes down, which cancels out here. So the derivative of the function with respect to Zi is simply this. So df dzi is easy. Now let's do, now we want to find dzi dw, right? So what was Zi? Now we want to find the derivative with respect to w. And that's easy. With respect to w, since this is a linear term, w simply cancels out, leaving us xi. So this is dzi dw, df dzi. If you just multiply them together, then this is the derivative. Okay? All right. All right, next thing we're going to learn is this thing called the indicator function. An indicator function looks like this with that 1, okay? And the way it works is indicator condition comes with, this is not necessary. Sometimes it's just this and C. So the way it works is that C gives you a condition. If a condition is satisfied, then the function will return 1. And if it is not satisfied, then return a 0. So this is essentially what this function does, right? And an example of that would be x is less than 4. So if for some reason, when you put x in, x is greater than 4, then the condition is not met, 0. If x is less than 4, the condition is met, then you got 1. So this is called an indicator function. we'll be using this. This is actually used a lot in neural networks. Okay. All right. The next function we're going to call, it's called a ReLU function. The ReLU function. This function is the key function in modern neural networks like ChatGPT. Like ChatGPT uses this function um, basically everywhere. So, so the ReLU function looks like this. If you have a function, or you can write it two ways, it's a function, but sometimes we write ReLU of x. When you put x in, it turns out that if x is greater than 0, then you're just going to return x. So if it's greater than 0, 5, you would just get a 5 here. 7.5 will get 7.5. All right. So, however, if it's any value below 0, you're just going to get 0. So that's what the ReLU function does. Any function above 0, you get x back. Any function below 0, you get 0. Now, by looking at the ReLU, you can guess what the derivative here is, right? Remember, the derivative tells you whether the function goes up or down at a given point. Since the function is not going up or down anywhere here, anywhere below 0, we know already that the derivative must be 0 when x is less than 0. And since over here the slope is equal to 1, right? It goes here by 1, goes up by 1. Since the slope is equal to 1, the derivative must equal to 1 for any x greater than 0. Therefore, given what we learned previously about the indicator function, it's basically an indicator function. So the derivative is an indicator function where if x is greater than 0, then it returns a 1, right? If it's less than 0, it returns a 0. So the derivative of a ReLU function is equal to an indicator function. All right, now let's see if we can take what we just learned about the indicator function and the ReLU function and see if you can find the derivative of this. Okay, so this is a ReLU function, but instead of x, we have w transpose x. So this is a linear function. All right, pause the video. Let's see if we can do it. All right, I also wrote the solution for you, so if you're stuck. All right, the next one we're learning is called the L1 norm. We learned L1 norm previously, but now we're going to learn to take the derivative. Now, the derivative of L1 norm, where x is some kind of two-dimensional vector. Now, you remember, what does L1 norm tell us? Well, if you are going around the block, right, it will go this way and then go this way. So the L1 norm is the summation of all the elements. So it'd be 1 plus 3. So you could, which is equal to 4. So basically, the L1 norm, given a vector of 1 and x1, x2, is the absolute value of x1 plus the absolute value of x2. Okay? That's the L1 norm. Now, if we want to take the derivative one variable at a time, we're going to take the derivative with respect to x1. So therefore, x2 is gone. So we're really just taking the derivative of the absolute value of x1. Now, what does the absolute value function look like? It looks like a v, right? Because, well, 2 is just going to give you 2, but minus 2 will also give you 2. So absolute value function is a v, telling you that the derivative anywhere below 0 is negative 1 because it's going down, right? It's negative, it's going down, and at the rate of 1. And any value above 0 is just 1. So the derivative with respect to x1, it simply depends on whether x1 is above 0 or below 0. Okay, so the derivative for the absolute value is 1 if x is above and negative 1 if it's below. And the function that signifies this is the sign. So if you put x in here and it's positive, then it's going to return a 1. If it's negative, it's going to return a minus 1. So an absolute value for sine for absolute, sorry, the derivative for the absolute value is sine. Okay, so this implies that when we take the derivative with respect to x1 and x2, it's simply the sine of x1, sine of x2. You can pull sine out, so it's just sine of x. So if you have sine of like -7 and 4, right? So this will be -1 and 1. Okay, because that's a minus and that's a plus. Over here, sine of 2 and -3, so 1 and -1. Okay, so that's the L1 norm. All right, since we did the L1 norm, let's try another one. Here's another exercise. Find the derivative for the L2 norm. Now remember the definition of L2 norm, right? If you have two dimensions, the definition of L2 norm is x1 squared plus x2 squared and the square root of that. So now pause the video, see if you can find a derivative of L2 norm as well as the derivative of the L2 norm square. Okay? All right, pause the video. We're going to do this exercise as the next exercise. No? All right, I wrote the derivative out here for you for the L2 norm. L2 norm square should be really easy. Hopefully you guys didn't have any trouble with that. All right. So the next exercise we're doing is, yes, the next objective is called the Gaussian maximum likelihood estimation objective. It looks like this. Now, this looks really, really complicated, but in reality, it's actually really, for one, it's a single variable. So mu right here is just a single variable. So this is a single variable equation. There's a multivariable equation version of this, but like don't worry about that. Now, even though this looks really complicated, if you were to know all the log tricks involved, we can actually simplify this into a really, really simple, very simple function. Okay, so these are the log tricks you need to know. First of all, this symbol here, that means product. So if you have something that looks like this, that means you're going to plug in I 3 times from 1 to 3. And you're just going to multiply them together, implying that if you have xi, right, instead of sum, like sum, we're going to have product. So x1, x2, x3, multiplying all three together. That's what that means. Okay. All right. So that's the first rule. The second rule is when you have x multiplied together, inside a log, you can actually split the log. Okay. So notice how we split the log into x1 and x2. This essentially lets us know that if we have log of multiplication of them, we can also split them. So log of three x's multiplied together is therefore log of x1, log of x2, log of x3. That was what we learned previously. So if we combine log and a product together, then the three logs becomes a summation. So sum of log of xi, 1, 2, 3. This leads us to the conclusion that whenever we have a product symbol that looks like this, we can move it outside and turn it into a sum. And whenever we have a product symbol outside the log, we can turn it into a summation outside of the log. So here is inside the log, here is outside the log. Okay. Lastly, two more properties. If you have log of x to some power, you can simply move the power to the front. So 4 times log of x. And the last one is natural log of e is equal to 1. Okay, so these are the rules. If you somehow know all these rules, combine them together, this equation that looks scary and complicated could be drastically simplified. All right, so how do we do that? Well, let's look at this first. Well, there's a product. The first thing was we can move the product outside and turn it into a sum, right? So we can move the product outside, turn it into a sum. So that's what I did. move this outside. So the product is now turned into a sum. Next, when you have multiplication of two variables, well, we can split them. We can split them. So we split into the first one, and then log split into the second one. After we split them, remember we're taking derivatives, right, with respect to mu, which means anything without mu is going to get canceled out. Notice there's no mu here. So we don't really care about this one. So that's gone. So we only really care about this term here. Next, remember when we have log of x to the fourth, the power moves to the front. So if we move the power to the front, then we end up having the power to the front log of e. And since log of e is equal to 1, which is another property we did, this cancels out, resulting in a much simpler notation that is just this. So taking a derivative of this with respect to mu is now much, much simpler, right? So we can pull the constant out. So we're really just taking the derivative of what's inside here. And that's really easy, right? We can find a derivative of this pretty easily, which is just equal to this. So taking the derivative of this may seem complicated at first, but a lot of things cancel out, and it turns out to be just this. Okay? All right, so let's take everything we learned using that Gaussian maximum likelihood objective and see now, pause the video, if you can solve this one. This one is the uniform distribution on the maximum likelihood objective. And yeah, see if you can solve this. I think I also provide the solution for this one. Yes, I did. All right, so try to do it yourself and see if you can do it. All right, we're going to continue. All right, so we previously learned that when we do find the derivative of single variate equations, we could basically use AutoGrad to check our solution to see whether the solution is correct or not. Now we can also use AutoGrad to check multivariate derivatives, right? So over here is an example. So and we do exactly the same thing. The same thing is basically we're trying to find the derivative of this. So we define the function here. Once we define the function, we simply put AutoGrad, automatically find the gradient, and then we can compare the result from your theoretical solution as well as Python's. And ideally, they will be the same. Okay, so here is an example of how I did it. This one is for this equation. I did another one for a pretty complicated equation, which you can see they are the same. So I mean, the idea, since you've done it already, like with one variable, the extension to multivariate should be pretty easy. And I've given you like a lot of examples on how to do this. The only thing that's different, that's from single variate to multivariate, is that in AutoGrad, there are certain functions they did not make it work the same way. So when you use AutoGrad, this transpose symbol doesn't work anymore. X dot t. You have to use x transpose x. Also, x dot y doesn't work anymore. You have to do np dot xy. So they changed a couple functions around, but and there are a couple other ones. So when things don't work, this is probably the issues that you're running into. Okay. All right. So lastly, let's consolidate what we've learned today. Okay. So to consolidate, you want to do all these, solve them by hand, and then write the code. Write the code to confirm you're correct. Confirm you're correct. Okay. These should not be that difficult. Okay. So I think that's it. That's the end of the day. There was a bonus one. I solved this for you. This is one of the equations. Um, I leave the answer to you guys for the homework. So it will help you if you guys are really stuck. So okay, that's it. I will see you in the next lecture.